Alright, so our next topic is going to be a new type of sequence called geometric sequences. In the previous section, we talked about arithmetic sequences, which was just the case where you start with a term and you add a constant to each new term. Okay, it's the same constant every time. We called it the common difference. Okay, well, geometric sequences are similar except we use multiplication instead of addition. Okay, so for a geometric sequence, the formula is going to be very similar, except instead of adding here, instead of adding a d, we're going to multiply by what we call an r. So it's r times a sub n minus 1. So instead of a sub n minus 1 plus d, it's a sub n minus 1 times r. It's again just a common multiplying factor. Okay, it's going to be the same number every term. Yeah, and so the reason we call it r, we had d for difference before, common difference. This is going to be a common ratio. It's a ratio because if you divided both sides by the a sub n minus 1, it'd be the ratio between a sub n and a sub n minus 1. So it's a ratio, common ratio. Now what's interesting is just like in the arithmetic sequence, if you were to continue to multiply every successive term by r, then at the end, at the a sub n term, you will have one less r than the number of terms there are. And so another way to write this would be to say a sub n is the initial term, a sub 1, multiplied by, well, n minus 1 r's. Well, if you multiply by r times r times r times r times r n minus 1 times, it's an exponent. It's r raised to the n minus 1 power. Okay, so these are the two formulas. They're structured very similar to the arithmetic formulas, except again, we're multiplying instead of adding here, and we're multiplying instead of adding here. Oh, and then instead of multiplying, we're doing an exponent. Okay, but everything else is essentially the same. Now let me give you an example. In the last video, we talked about the example where the n values, again, 1, 2, 3, 4, 5, 6, and then they keep going. And then the a sub n's, in the last video I started off with a 2, and we made it grow or increase by 5. Well, here I'm going to multiply by 5, show you kind of how this works out. So instead of adding, we're going to multiply. Well, multiply by 5, you get 10. Multiply by 5, you get 50. Multiply by 5, you get 250. Multiply by 5 again, you get 6 something. No, you don't. Wait, multiply by 5. What's 250 times 5? Or, yeah. I'm checking this out. Oh, it's 1250. I'm way off. That's 1250. And then 1250 times 5. I just froze up on that one. Times 5. Let's see. 6250. Okay, and so that's getting way bigger, way faster, right? Because you're multiplying instead of adding. All right, but again, each one is a multiplication by 5 here. And so the common ratio from one to the other is 5. So if you were to divide one term by its previous term, you'll always get 5, right? 250 divided by 50 is 5, and so forth. So we have our common ratio. Now let's say I wanted to find the 20th term. Well, it was enough just to find the first 6, but if I wanted to go up to 20, I just need to do this. Go a sub 20, use this formula, is equal to a sub 1 times r. Oh, we already know what r is. We'll come back to that. To the n minus 1 power. Well, that'd be the 19th power. So a sub 1 is 2. R is 5, so it's 2 times 5 to the 19th power. Okay? 2 times 5, and I'm using my calculator to do this off to the side so you can't see it, and I get a huge number. In fact, it might even be worth showing this. So I get 2 times 5 to the 19th is 3.814 E13. That means this is scientific notation, meaning times 10 to the 13th power. I'd have to move that decimal 13 places to the right. So this is a big number, right? It's approximately 3.8 times 10 to the 13th power, but obviously I'm rounding. There's tons more decimals here. Okay. This is a number so big your calculator can't really handle it without rounding. It rounds it off after 9 digits. Or 10, 9 or 10, somewhere in there. Okay? So that's just the 20th term. Let's say you wanted to go to the 100th term. Then you're looking at some huge number. Okay? Okay, so now we're also going to try and prove that a sequence is geometric. We did this with arithmetic sequences last time. And so let's try to prove that 3 to the 2n is geometric. Okay? We're going to try to prove that. Okay, maybe it is, maybe it isn't, but if it is, we'll prove it. And so what we want to do is we want to try to take the ratio of any two terms, right? This one divided by this one, or this one divided by this one. It doesn't matter, any two terms, the ratio should be that fixed value of r. Now, here it was 5, but here it might be something different. So what we want to do is we want to prove that. So we're going to take a sub n, which is 3 to the 2n, 3 to the 2n, and we're going to take a sub n minus 1, that's the previous term, which would be 3 to the 2 times n minus 1, or if I distribute the 2, it's 3 to the 2n minus 2. And I want to show that the ratio between those two things is constant. Right? So if I take a sub n and divide it by a sub n minus 1, I should get a constant if this is a geometric sequence. So I take 3 to the 2n over 3 to the 2n minus 2. Alright, well, remember, I'm going to use some exponent rules here and just kind of simplify this. Exponent rules will become very important here. Okay, remember, if you've got two powers like this, you can split them up. Or if your powers are being added or subtracted, I could think of this as 3 to the 2n times 3 to the minus 2. Gosh, I can't write that. Okay, right? Because if you have a product with the same base, you can add their powers. So 2n and minus 2 make 2n minus 2. So going the opposite direction. And then, well, I can cancel common factors, right? 3 to the 2n cancel out. I'm left with 1 over 3 to the minus 2. Well, a negative exponent becomes positive in the numerator, right? If it's negative in the denominator. So this becomes 3 squared, which of course is 9. Because 9 is a constant, we know that it is a common ratio because it occurs for every pair of consecutive terms. It doesn't matter what they are because I just use general numbers n and n minus 1. Right? So we'd say that 3 to the 2n is geometric because consecutive terms have a common ratio? Of 9. I'll even include the specifics.